Einstein's relativity is commonly thought to be really difficult to understand, but it doesn't need to be. Before Einstein, we thought that distance was absolute. Say a volcano goes off in Italy, and then 10 seconds later, we observe a solar flare on the sun. We can measure the distance between those two events, and everyone would agree on the distance. It doesn't matter if we're measuring them from our position on Earth, or if we are zooming away in a spaceship at 1,000 miles a second. Einstein's big breakthrough, though, was that space and time aren't separate at all, but they're fundamentally linked. And that what is invariant is not the distance between two events, but a combination of both the distance and the time. Let's take that example again. For me, sitting here on Earth, I might see the volcano go off and then 10 seconds later observe the solar flare on the sun. But now the person who is in a spaceship moving away at 1,000,000 miles a second, in between those two events, they would have moved proportionately farther away from both the sun and the Earth. And so the light from the second event has to travel a greater distance and then has to take proportionately a longer time to reach them. They would measure a greater time interval between these two events. The distance they would measure between those two events would actually be contracted. It would be shorter. Now, these are effects known respectively as time dilation and length contraction, but really they're both just a result of this fundamental thing called the invariant. That what is fixed is not distance, but a combination of distance and time. And that shows us how it is not space and time separately that exist, but a combined space-time that exists. Now, the last thing we have to discuss is general relativity. In general relativity, space-time is not flat like it is in special relativity. It's not the same everywhere. Rather, it's curved. And it's curved because of the mass distribution of the universe. It's like having a rubber sheet with a load of different weights on it. Those weights will cause the sheet to bend and stretch in different ways in different places. And that's what space-time is like throughout the universe. And so in general relativity, we make the farther leap that it is not the invariant in flat space-time that's conserved, but it's the invariant in this curved space-time. And that's it. Newtonian mechanics, special relativity, general relativity are all fundamentally the same theory. It's just they disagree on what is invariant, on what is conserved between every observer.